So in this design advisor, you can Google design advisor MIT, and you have this. Okay, so this is a design advisor MIT, and that's the website. Okay. So we have this website. Then here we have the setup and the results. First, we have to do the setup, and I think I did this before, but I'm going to do it again. So we have to select the region. Let's go step by step. If we select this region, it has to be USA. If we select the city, we don't have Keene, New Hampshire. Do we have anything in New Hampshire? No. I think we have Boston. Okay, so let's select Boston. It's colder here, but I mean, if it's close enough, it will work. Occupancy. Choose an occupancy type or select options manually. Here we can select assembly, classrooms. I think I will do it manually. We have the schedule. So the schedule, it's 8 a.m. to 7 p.m. Okay, we go from 7 a.m. to 7 p.m. I don't know, but we have to use the same schedule that we have used in Revit. Okay, so if in Revit we are here and we go to the space, and in the space type we have selected this occupancy schedule. Well, it's from 6 to 10, but these first few hours until 8, and then after 7 there's almost nothing. Okay, anyway, we have to select the schedule. In terms of selecting a schedule, Revit seems more accurate because we have these options. Do we have those options in Design Advisor? I don't know. We have the person density. Here again, if we change the units, some units change and some units don't. So we have to work per square meter. Anyway, this works. It's 7 a.m. to 7 p.m. And then here we need the person density. So the person density, in this case, if we have let's insert and we have person density. So the person density, it's people. Let's see the units. It's people per square meter. So that is people divided by the area. So we have 26 person or 26 people, and divided by the area. If I select the area of around 600 square feet. Okay, so that would be the people density, 26 divided by 600. So that will be 0.04 per people divided by square feet. But now we have to do this in people divided by square meters. So we have to turn square feet to square meter. We need to convert. So here we have 600 square feet. So this is around 56 square meters. So the people density, it will be 26 divided by 56 square meter. So the area here is 26 divided by 56. It's a 0.46 people per square meter. Okay, so that's the value that we have to type here. 0.5. It's 0.46, so it's around 0.5. That's the density. Here we have lighting and equipment. We haven't taken that into account, or in Revit, when if we see that this is an office building, here we have the lighting schedule, and here we have the power schedule, and here we have the lighting load density. Okay, and so here we have a lighting load density in watts per square feet. The problem is that here we have in Design Advisor, we have lux and watts per square meter. Lighting, this 400 office work, we can rely on this, because when we are designing a building, 400 lux, it's the average light that we have. Okay, so to work well and to see things on the table and can read the paper or book, we need from 400 to 500 lux. We're not teaching lighting if we don't have time. But anyway, this is the average value, so it's good. We can keep this one. And then the equipment is the amount of computers, the amount of lights that we have here. So if we are designing an office building, we can do this. Here we have office light, medium, or high, or no equipment. No equipment is not an option. So what would be the equipment here? What's the density? The power load density. Okay, so according to Revit, we have 1.3 watts per square feet. So we have to turn this into watts per square meter. So I'm sure that there is another converter, watts per square feet to watts per square meter. Right. Okay, so here we have watts per square feet, it's 1.3. If we convert, this is 13 watts per square meter. So according to the Design Advisor, we have 5, and it has to be around 13, 14. So that will be 15. Okay? So it's a medium high office, to be consistent between Revit and this Design Advisor. Then the ventilation system. We have the mechanical cooling and heating. We have natural ventilation cooling and mechanical heating, and natural ventilation cooling and mechanical heating. That will make a difference. Okay, so let's do this, but when we run the second scenario, we're going to change this to natural ventilation for cooling, and it will drop the value a lot. Okay, so let's but first select mechanical. Then the indoor temperature maximum 78, minimum 68. I think this maximum is too much. Let's say 75 and 68. Okay, so the average is around 70, but this is the maximum. The maximum indoor temperature is the temperature at which the air conditioning starts working, and the minimum temperature is the temperature at which the heating system starts working. Okay, so we can type 70 for both, but it's not realistic. In winter, we set the heating point below 70, and in summer, we set the cooling point above 70. So 68 and 75, it works well. The maximum relative humidity, 60, good. The ventilation rate, we have liters per second and per person. So that's another, we have in Revit, we set 20 CFM, cubic feet. So 20 cubic feet per minute. Per person. And now we have to set liters per second. So we have to convert again CFM to liter per second. Cubic feet per minute, it's 20. Liters per second is 9 or 9 point something. Okay, so let's do it here. It's 10. Okay, so we have 9 point something. So let's say 10. And then the air changes rate. If we okay, yeah, I don't remember. I didn't remember that. It's the same. So if we change this 10 liters per second, it's 6 air changes per hour. Okay, thermal mass. We will run a different scenario with this. So that depends on the construction type. High thermal mass means that we have concrete slabs. Lightweight will be residential buildings. So I would use high thermal for commercial, low mass for residential. But then we will test a different scenario with this. Okay, so let's select high. Building geometry. We have 4 facades. Okay, so it's not just an attached building, will be a one facade building, but here we have 4 facades. And unmixed air between zones. Since we have internal walls and doors, we will select this option because our building, it's not. Okay, so mixed zones will be, if we didn't have any partitions, it will be mixed, but we have clear partitions. So we are selecting that one. Building geometry. So we have the entire floor, yes. Building orientation, it's north, south, east, west. And then we have the feet. I don't know, it's around 31 by 20, kind of. So it's 31 feet by 20 feet. Roof description, don't consider roof. Yes, consider roof. We have modified bitumen roof, cool roof, or green roof. It's not green. Let's select this option, the first one. And then roof insulation, choose an insulation or an R value manually. So the R value, it's BTU hour square feet. Okay, so what's the R value of this roof? It was 52. Floors, 1 floor. Well, if you select this R value, you don't have to select any of those. Okay, we enter the R value manually. Then typical room properties, room dimensions. Well, we have here the building geometry. Okay, so that's the plan, the building, the floor plan. But here we have typical room properties. What we have in this building, we have 4 rooms. And what is a typical room dimension? The average. Okay, so if this room is 14 feet by 9, this is slightly bigger, that's slightly smaller, but we can say that it's 14 by 9. So the room dimensions, the width will be like 14, the depth will be 9, and the height, it's height. Around 10. Window primary facade orientation. That is the orientation of the facade with the largest window area. I think in this case is south. So I will say south. Or we can say southeast. Yeah, because most of the glass it's in the southeast. Okay, so let's say southeast. And now we have the window description. The window area. This is the window to wall ratio. Okay, so that's the that should be in some of the reports that you have done. Okay, so the window to wall ratio, it's 80%, according to this report. So let's say 80%. And now we have to select a window type. We are going to select triple glazed, and it doesn't include blinds. Okay, so for the second analysis, we will include blinds, and that will reduce the solar gains. But let's select triple glazed, glass type, low emissivity, and overhang. We don't have any overhang. And wall description, we are going to enter the R value manually. So what is the R value of the wall? It's 44. So we are done. So let's run the first scenario. So that's the first report. And I'm going to write down the total yearly and cooling energy. So for the year, for the heating and cooling, yeah. So for the heating, we have 151.6 units, kilowatt hours per square meter. Cooling, it's 232.6 kilowatt hours per square meter. Okay. Can we turn this into BTU? Since we have here in kBTUs per square feet. So let's try to do it. We have to convert a kilowatt hour divided by square meter to kBTU divided by square feet. This is kilowatt and this is BTU. I think it will be correct. So if this is 151, so that will be 13. And the other one, uh, 232. Let's try another conversion. because I don't trust it. Energy intensity conversion tool. Okay. So I rely on this website better. So this is 151.6, and this is 48 kBTU per square feet. Okay, so that's 48. The other one was wrong. 48 kBTU divided by square feet. And that one is 232. That's 73 kBTU divided by square feet. So we have 48 for heating, 73 for cooling. What is the criteria? Again, we are good at heating, but we are not that good at cooling. So it's 73, and here we have 50.